Good morning, dear students. So, our next unit is unit number 2, which is network models. And in this topic, we are going to learn how to formulate transportation problems, transshipment problems, and assignment problems. Uh, let us start with the topic of transportation problem. The transportation problem is a classic optimization problem in operation research and supply chain management. It involves determining how much to transport from each supplier to each destination in order to minimize the total cost, considering the supply capacities of suppliers, demand requirements of destinations, and the cost of transportation between them. Let us take an example, a simple real life example. Let us say you want to you are a manufacturing company of some IT products. Let us say uh, keyboards and pen drives. Okay, and you want to and you have a contract with distributors, and the distributors will then ensure that whatever products you are manufacturing are supplied to different IT shops. So, as a distributor, the person has to take care of what is the supply that he will be getting from the company, and also he needs to know that what is the demand in the market for those products. So so as he figures out what is the demand and what is the supply from the market and the manufacturing company respectively, he also needs to figure out that how much is the cost which is associated when he supplies one unit of, let us say, keyboard and one unit of pen drive from the manufacturer to the different shops, so that he can minimize the total cost of his entire distribution operation. So this is what we will learn in transportation problem. Now let me take a simple example to elaborate what I just discussed. In this case, we have an example based on Santa's gift delivery challenge. Okay, so Santa has three toy workshops. One is Toyland, one is Funcraft, and another one is Play Magic. And he needs to deliver toys to these four cities, namely Snowville, Jingleburg, Twinkletown, and Dream City. So three origins are there. That is Toyland, Funcraft, and Play Magic. That is the workshops, toy workshops, and the four destinations are there. That is the cities to which Santa has to deliver. That is Snowville, Jingleburg, Twinkletown, and Dream City. Now each toy workshop makes unique toys, and Santa wants to figure out the best way to deliver them, making kids happy while keeping the things cost effective. Okay, so this is the problem. Now, what you are seeing on the screen is the delivery cost matrix. So you can see over here in the columns there are four different cities, that is the destinations to which the toys from the origin are supposed to be distributed. And in the rows you can see this is the Toyland, that is the first row, that is the first workshop. Second workshop Funcraft, and third workshop is the Play Magic. Right, and in these columns are those four cities, that is Snowville, Jingleburg, Twinkletown, and Dream City. So whatever you are seeing in between these top row and this first column, uh, that is these values CTS, CTJ, CTT, CTD, and so on. Those values depict the cost of delivery from one toy from the origin to the destination. Again, I'm repeating these uh, elements of the matrix, that is CTS, CTJ, CTT, CTD, CFS, CFJ, CFT, and so on. They represent the cost associated for the delivery of one toy from the origin, which is the first subscript T, to the destination, which is the second subscript S. Okay, so T stands for Toyland, S stands for Snowville. So the cost of delivering one toy from Toyland to Snowville is what? CTS. Again, the cost associated of delivering one toy from Toyland to Jingleburg is what? CTJ. Similarly, the cost associated of delivering one toy from Toyland to Twinkletown is what? CTT. The cost associated of delivering one toy from Toyland to Dream City is CTD. Okay, so this is what we mean by the uh, cost delivery matrix. Now, the second matrix that we are seeing on this slide is the quantity matrix. Okay, so if you can see over here, the first column that is of the workshops, that is Toyland, Funcraft and Play Magic. And in the second column, it is depicting the supplies that are obtained from these respective workshops. That is the amount or the quantities of toys that are being supplied from this workshop Toyland is how much? ST. The quantities of toys that are supplied from the workshop Funcraft is what? SF, and the quantities of toys supplied from the workshop Play Magic is what? SP. Okay, so this is the supplied quantities. All right, so you can like for an example, if I say that 100 toys are being manufactured and supplied from Toyland. So that is Santa is 100 toys from Toyland. So ST will be what? 100. Likewise, if Funcraft is manufacturing and supplying 150 toys, then I will say SF is having 150 toys is equals to 150 toys. So Santa has 150 toys from the Funcraft. And similarly, the third workshop, Play Magic, it has 120 toys. So Santa will have 120 toys from the Play Magic. Okay. And this matrix that you are seeing on this slide, that is known as the destination matrix. Okay, sorry, demand matrix. So basically, what does it mean? It means that what is the demand or what are the number of quantities that are being demanded demanded in those four cities. That is Snowville, Jingleburg, Twinkletown, and Dream City. Okay, so if you can see over here in the second column, it is representing the toy demand. All right, so that means the demanded quantities from Snow Village City is how much? DS. DJ means what? It means the demanded quantities from the city Jingleburg. DT is the demanded quantities from Twinkletown, and DD is the demanded quantities from Dream City. So if Snowville has, let us say, demand of 80, then we'll say that Snowville wants 80 toys. Jingleburg likewise wants 100 toys, and so on. Okay, so up till now, what we have learned? We have learned uh, the first matrix, which is the cost of delivering. There is a cost matrix, that is what? Cost of delivering one toy from the origin to destination. We have also learned the supply matrix or the quantities matrix, that is the quantities or the supply from each of the workshops. And this third matrix, that is the demand matrix, that is representing the amount of quantities required in these four cities. Okay. Now, this is the simple delivery plan. What are your decision variables? That is, from each of these three workshops that Santa has got, and from those workshops, he is supposed to deliver the toys as per the supply from these three workshops. He is supposed to take care of the demand of toys from those four cities. So how he will ensure that what quantity of toys he will take from each of these three workshops and will satisfy the demands of all the four cities? That is the decision. That quantities is your decision variable. Okay, so the decision variable is your number of toys from your ith workshop or the origin to jth city, yeah, to j destination, and hence it is represented as xij. So your I, first subscript I represents what? It represents the origin, yeah, workshop, and second subscript j represents city or the destination. Okay, so if I say x 1 2, so that means your quantities of toys from the origin 1 to destination 2. Okay. Now, what do you mean by objective? What objective function? We already know that that is the crux of the problem, that what is your final outcome that you desire. So in our case, we want to minimize the total delivery cost, right? So if you can see over here, there are two summation symbols. These are called summation, capital Greek symbols. So these are the Greek symbols, capital sigma. So so basically, what does they represent? They represent the sum of the quantities. Now, how to understand this symbol? It is trying to tell you that what will be the total cost. Now, how to understand that? So if you see over here, there are two variables, there are two symbols, Cij and Xij. Now I and j, you already know that what do we mean by I and j. I, first subscript I is the origin or the workshop in this case, and the second subscript j is basically the destination or the city in this case. Now, and same applies for this ij that are associated with capital C. Now, and xij together means what? It's the number of toys from ith origin to jth destination. But if I'm saying that I want to minimize the total delivery cost, then I need to know that what is the costing associated with a unit of toys being supplied from ith origin to jth destination, right? So if I'm saying that I'm delivering, I'm supplying xij quantities from ith origin to jth destination, then the cost associated with that number is what? It is the quantity, it is the cost, that is Cij. So that means Cij is the cost associated for supplying and delivering one unit of the product from ith origin to jth destination. Am I clear? I'm again repeating. Cij is what? It is the cost associated with delivering one toy from the ith origin to the jth destination. So if, let us say, 2 rupees is the cost associated from ith origin to jth destination, and if I am delivering 10 toys from ith origin to jth destination, then my total cost will be what? 2 times 10, that is 20. And when I repeat this process for all the values of I and j, and that's where I need to apply this sum operation, that is this Greek symbol capital sigma. Okay, so this is the meaning of your objective function, that is double sigma over I and j respectively for Cij times Xij. Now let us see how to figure out the constraints. Now, like in the first unit, we had number of different constraints of the type less than or equals to or greater than or equals to or equals to. In a similar way, over here we'll be having two types of constraints, that is a supply constraint and a demand constraint. Okay, so effectively what we are saying, that the supply has to meet the demand. Let us see how. Now, if you can see over here, Santa cannot see whenever you are supposed to meet the demand, you must ensure that the supply is sufficient, right? Because you cannot go over the board if you are to do a delivery. You cannot deliver more than what you are producing and supplying, isn't it? So Santa cannot deliver more toys than he has from each of the workshop, and each city gets the right number of toys they wish for is the most important part of his delivery operation, right? And also there can be no negative toy deliveries. Okay, so with respect to these conditions, we have the first constraint, that is supply limits. Now, how do you write it? It's quite simple. The summation of all the quantities from ith workshop to jth destination. Okay, that should be less than or equals to Si, where I is what? Either it is Toyland, Fun Park, or Play Magic. That is the three toys workshop. Is this clear? Again, I'm repeating. So your supply constant is what actually? It's the summation of all the quantities of your toys from ith workshop to the jth destination, and that should be less than or equals to Si. That is the total supply coming out from that particular workshop. Okay, so your I will be what? Either the first workshop Toyland, or the second workshop Fun Park, or the third workshop Play Magic. Okay. Similarly, what should be your demand constraint? So it basically means that sigma xij should be equals to dj. That is a demand from the from each of the cities. So your j will have values what? Uh, Snowville, Jingleburg, Twinkletown, and Dream City. Okay, so these are your four cities or the four values that your parameter j can take. Okay, so that is the meaning of your demand constraint. And lastly, we have non-negative deliveries. There is no non-negativity condition. So your xij, that is the total number of quantities from ith origin to jth destination, cannot be less than 0. It has to be greater than or equals to 0. Where I is what? It can take three values, that is TFE, that is your workshops, three workshops, and J can have different values of SJTD, that is the four different cities. I hope this is clear to all. Now let's see how. Okay, I think I already written it over here, so I'll just use this. If you want to refer it, you can refer the previous slide. That is slide number. I think it was slide number 6. Okay, so in that we have specified. So this is the quantity that is associated for the first workshop, that is Thailand. So we are supplying 100 toys from that workshop, and we are supplying 150 toys from the Funcraft workshop and 120 toys from the Play Magic workshop. So and how, so these are the supplied quantities from the respective workshops. And likewise, what was the demand from those four cities? uh, Snowville has a demand of 80 toys, Jingleburg has a demand of 100 toys, Twinkletown has a demand of 70 toys, and Dream City has a demand of 120 toys. Okay, so now if I want to figure out the supply constraints, I will write it in this way. So supply quantities, right? So it should involve the variable x, that is a decision variable x. Now, and it will have two subscripts, one for the origin and second one for the destination, that is from workshop to the city. So what are the quantities of toys that are going to be supplied from Toyland to the four cities? Because basically there are three workshops and four cities. So as a distributor or as a Santa who is going to deliver the toys from the workshop to four different cities, uh, he will think in which way. He will think that okay, how many quantities I can deliver, I can have from the toilet workshop and get it delivered to all these four cities, right? So that is what it is, xts, that is quantities of toys from the Toyland workshop to Snowville, plus quantities of toys from Toyland to Jingleburg, plus quantities of toys from the Toyland to Twinkletown, plus the quantities of toys from the Toyland to Dream City. Okay, but how many quantities in total Toyland can supply? That is 100. So obviously he cannot deliver more than the supply, right? So that is the reason we are having a less than or equals to inequality over here. Okay, I hope this is clear to all, that why do we have a less than or equals to inequality for the supply constraint over here. Okay, again, if I take the second workshop, that is Funcraft, then what is the supply quantities to these four different cities from the second workshop Funcraft? That will be what? The quantities X from Funcraft to Snowville, quantities X from Funcraft to Jingleburg, quantities X from Funcraft to Twinkletown, and quantities X from the Funcraft workshop to Dream City. And what is the supply limit of this Funcraft workshop? It is 150, right? So it cannot supply one more than 150 toys to these different four cities. So that is the reason again we are having less than or equals to symbol. Okay. Again, for the third workshop, what do we have over here? XPS, that is the quantities of toys supplied from Play Magic to Snowville, quantities of toy from supplied from the workshop Play Magic to Jingleberg, quantities of toys supplied from Play Magic to Twinkletown, and quantities of toys supplied from Play Magic to Dream City. Again, it cannot supply more, it cannot deliver more than what it is supplying. So it has to be less than or equals to 120. Okay, so the reason again, like we discussed, is it cannot for less than or equals to a constraint is what, that it cannot deliver more than what it is supplying. All right, so this is what we mean by the supply constraint. I hope this part is clear to all. Next type of constraints are the demand constraints. Okay, now what do you mean by the demand constraints? It basically represents that how many quantities are being of a toy are being demanded from each of the four cities. Okay, now if you see this demand constraint, for this demand constraint, what is the demand values from the respective four cities? We've already discussed this, that Snowville is demanding 80, Jingleberg is demanding 100, and Twinkletown is demanding 70, and Dream City is demanding 120. So because the supply has to meet the demand, and that means that whatever we'll be supplying will be able to satisfy the demand. Okay, so that is the reason over here we are writing equality instead of less or equals to, so that we can make sure, we can ensure that whatever we are supplying on the left is actually equal to what has been demanded by that destination. I hope this is clear. Okay, so that by that what it means, that whatever I'm supplying on the left, that is, so in a very simple way I'm putting it this way, that for example if I talk about Snowville, now Snowville can have the supply of toys from which workshops. So it has three different options: Toyland, Funcraft, and Play Magic. So I will write in this way: the quantities of toys going from Toyland to Snowville plus the quantities of toy going from Funcraft to Snowville plus the quantities of toys going from Play Magic to Snowville should be what? Should be able to satisfy the demand it has. That is, it should be equals to 80. And that is the reason we have written over here like this, that XTS, that is the quantities of toy going from Toyland to Snowville plus quantities of toys going from Funcraft to Snowville plus quantities of toys going from Play Magic to Snowville is equals to 80. I hope I am clear to all. Again, quantities of, for the second city, Jingleberg, the quantities of toys going from the first workshop, that is Toyland, to Jingleberg is XTJ, plus quantities of toys going from Fun Park to Jingleberg is XFJ, plus quantities of toy going from Play Magic to Jingleberg is what is able to meet its demand, that is equals to 100. Okay, again there is third city, there is Twinkletown. So for it, what are the options to get the supply of toys in order to meet its demand? That is XTT, quantities of toys from Toyland to Twinkletown plus quantities of toys from Fun Park to Funcraft to Twinkletown plus quantities of toy from Play Magic to Twinkletown should be what? Should be equal with its demand of 70 toys. Likewise, for the last city, Dream City, quantities of toys going from uh, Toyland to Dream City, XTD plus XFD, quantities of toys going from Funcraft to Dream City plus quantities of toy going from Play Magic to Dream City should be equal to its demand of 120 toys. Okay, so this is the meaning of supply constraints and demand constraints. I hope I'm absolutely clear to all. And lastly, like we discussed, that the deliveries cannot be negative, right? So for I and J, that is for I equals to TFP, those three workshops of toys, and for J equals to these four different SJTD workshops, your I think over here the formatting is some problem, is having some problem. So it should be like this: X I J should be greater than or equals to 0. Okay, I think this xij and greater or equals to 0 are having space, so it has come below. But yeah, this is your non-negativity condition, where I parameter will take value of those three different workshops, that is T, F, P, and J will have the value of either S or J or T or D. Okay, so these are the three main elements of your constraint, that is supply constraint, demand constraint, and non-negativity constraints. So this is the entire L.P.P formulation, transportation problem formulation. First one is your objective function. So your objective is to minimize what? Your total cost. So minimize Z equals to, now what was the cost of one supplying one toy from the workshop toy craft, sorry, Toyland, to the source, that is the city snow village, that is TS. So that is XTS, that is the quantity supplied from Toyland to snow village XTS, and the cost associated with that supply, that one toy supply, is what? Rupees 10, right? So the total cost will be what? 10 XTS. Similarly, quantity supplied from Toyland to Jinglebug is what? XTJ, and the cost associated for sending one toy from Toyland to Jinglebug is rupees 8. So the total cost will be what? XTJ. Similarly, quantity is being supplied from Toyland to Tinkertown is what? XTT, right? So and the cost of supplying cost of delivering one toy from Toyland to Tinkertown is rupees 12. So the total cost will be what? 12x TT. Okay, so this is how you cover all the origin and destinations with respect to their costing, and you create a objective function. So these are the constraints that we just studied. That is the supply constraint, demand constraint, and the non-negativity constraints. Okay, so this is how you will write your non-negativity constraint xij greater or equals to 0. Okay, again I'm repeating over here. Your supply you cannot distribute more than what you are supplying. Okay, so that's the reason you are having less than or equals to symbol for your supply constraints, whereas for demand constraints your supply has to meet the demand, that is the left hand side of the quantity has to meet the right hand side demanded quantity, so it is showing equality. Okay, I hope this is clear to all. So this is uh, the transportation problem formulation matrix. Over here you can see we have written the supply quantities and this is the demand quantities. Okay, so whenever you have the supply column, you just calculate the values, that is 100 plus 150 250 plus 120, that is 370. And in the demand also you calculate the demand values, 80 plus 180 plus 70 plus 120, that amounts to what? That amounts to 370 as well. So that means it's a balanced transportation problem, that is your demand that has been given to you is equals to your supply. Okay, this is called the balanced transportation problem. Okay, so this is the network model. You can see that how many cities we have. We have four cities and we have three works. So four cities: Snow Village, Ingleburg, Twinkletown, and Dream City are your four cities on the right, and we have three workshops, that is Toyland, Funcraft, and Play Magic on the left. So these are your workshops. These are your workshops, and the lines that you are seeing over here is basically the routes, that is from Toyland to Snow Village, Toyland to Jingleburg, Toyland to Twinkletown, and Toyland to Dream City. And these green and the green values that are there on these lines, the arrows from Toyland to these different four cities, represents the cost associated of sending one toy, of delivering one toy from Toyland to four different respective cities. So that means 8 rupees per toy is the delivery cost from Toyland to Jingleburg. 12 rupees is the delivery cost from of one toy from Toyland to Twinkletown. 15 rupees is the delivery cost of one toy from Toyland to Dream City. Okay, this is how you will figure out the network model. So again, for the fun graph, we have these four different destinations with their respective cost for one toy delivery, and same is the case for the play magic. So you can see on the left hand side we have written the supply that this toyland can provide. It can provide at the most 100 toys. Funcraft can provide at the most 150 toys, and play magic can at the most provide 120 toys. Okay. uh, Similarly, you can see on the right hand side, the first city Snowville has a demand of 80 toys. Second city has a demand of Jinglebug has a demand of 100 toys. Third city has a demand of Twinkle Town has 70 toys, and last Dream City has a demand of 120 toys. Okay, so this is how you can represent your network model. Okay, so in the next session, we'll start with this problem of transportation. We'll see how we can formulate it using whatever we have learned in this session. Okay, thank you. I hope everyone has understood.